Welcome. Today we're going to talk about the basics of data structures. But before we get into the details, let's take a step back and talk about what data is and how we classify it. So, what is data anyway? It's basically everything on your device like numbers, text, images, videos, you name it. Just like how you use different tools for different jobs in real life, we need smart ways to organize all this digital stuff. Simple, right? Now, before we jump into the structures themselves, let's take a moment to understand data types. Think of them like different boxes we use to sort all our digital stuff. It's like the computer's way of knowing what's what. So, what kinds of boxes do we have? Well, first up, we've got integers. These are just whole numbers, like 11, 12, 33. No fractions or decimals here. Then we've got floats. These are the numbers with decimal points. So, 11.22 or 33.334, that kind of thing. Booleans are super simple. They're just true or false. That's it. Like a light switch, on or off. Characters are single letters, numbers, or symbols. So A, B, C, D, each of these is a character. And there are many more data types out there. Now that you have a good understanding of data and data types, we can finally tackle data structures. Data structures are clever ways we organize and store data in a computer program. Let's visualize this. On the left side, imagine a jumbled mess of data, like a pile of unsorted books. On the right side, we have structured data, neatly organized using data structures like stacks or queues, just like books arranged on shelves by category or author. Alright, let's break down the difference between data types and data structures. And hey, who doesn't love a good banana analogy, right? Think of it this way. The bananas themselves, those are our data. It's the actual information we're dealing with. Now, when we talk about data types, it's like labeling those bananas based on what they are. So, we might use a string data type to store the word banana. That's how we represent text. If we want to keep track of how many bananas we have, we'd use an integer data type, like the number 5. And if we wanted to answer the question, is this a grape, about our banana, we'd use a Boolean data type, which is just a fancy way of saying true or false, in this case, false, because, well, it's a banana, not a grape. So, data types are all about classifying what kind of information we have. Data structures, on the other hand, are about how we organize that information. It's like deciding how to arrange our bananas. We could use a queue data structure, which is like lining up our bananas, oranges, and apples in the order they were added to the fruit basket, or we could use a stack data structure. So, data structures give us different ways to store and access our data, depending on what we need to do with it. Make sense? Now that we've covered the basics of data structures, let's dive into some common ones. We can broadly classify data structures into two main categories, linear and nonlinear. Linear data structures are like a line of people, each person has a specific position in the line. Some common linear data structures include arrays, linked lists, stacks, and queues. On the other hand, nonlinear data structures are more like networks or hierarchies. Two common types are trees and graphs. Let's start with arrays. An array is like a neat row of boxes. Each box has a label on it, a number that tells you its position in the row. We call that label the index, and we always start counting from 0, not 1. So, the first box is at index 0, the second at index 1, and so on. The really cool part about arrays is how they live in the computer's memory. It's like having addresses for each box. Let's say the very first box, at index 0, is assigned memory location 101. Because arrays like to stay together, the next box, at index 1, will be right next door at memory location 102, and so on. They're all lined up neatly in a row, which makes finding a specific box super fast if you know its index. Now, let's talk about some variations of arrays. The most common type is the one-dimensional array. It's like a single line of boxes, all in a row or maybe stacked in a column. Let's say we want to store the letters A, X, H, and C. We could put each letter in its own box in a one-dimensional array. And remember, to find H, we just need its index, which is 2 in this case. Things get a bit more interesting with multidimensional arrays. Imagine a table with rows and columns. That's what a multidimensional array looks like. It's like having a whole bunch of one-dimensional arrays arranged together. To find something in this table, we need two pieces of information, the row number and the column number. So, if someone says, go to row 1, column 2, you'd end up at a specific cell in that table. Then there are jagged arrays, which are kind of like arrays within arrays. The catch here is that each row can have a different number of columns. Think of it like a bookshelf where some shelves are longer than others. It's a bit more flexible but can be a bit trickier to work with sometimes. Now, let's talk about dynamic arrays. To really appreciate these, we need to understand their more rigid cousin, the static array. Imagine a static array like a box of donuts. You buy it with a set number of donuts, and that's it. You can't squeeze in more donuts once it's full. So, let's say we have a static array with room for 3 elements. We try to add a 4th element. Nope, no space. It's like trying to fit that extra donut in the box, not gonna happen. Dynamic arrays, on the other hand, are like magical donut boxes that expand as needed. We start with, say, 3 elements, but if we want to add a 4th, no problem. The array grows to accommodate it. This flexibility is super handy when we don't know how much data we'll be dealing with beforehand. Finally, let's talk about associative arrays. These are a bit different. Instead of using those numerical indices like 0, 1, 2 to access elements, we use unique keys. Think of it like a dictionary. The word you're looking up is the key, and the definition is the value. So, in an associative array, we might have a key called name with the value John, and another key called age with the value, say, 30. It's a way to store information in pairs, making it easy to retrieve values based on their associated keys. Alright, let's dive into a new data structure, the linked list. Imagine a chain. That's a good way to visualize a linked list. Each link in the chain is like a node, and each node holds a piece of data and a little connector that points to the next node in line. Every linked list has a starting point, a special node called the head. It's like the very first link in our chain. From the head, we can follow those connectors, those links to the next node, and then the next, and so on. Eventually, we'll reach the end of the chain, which is marked by a special, null value, kind of like saying, okay, this is where the chain ends. Now, let's break down those linked list types, starting with the singly linked list. In a singly linked list, each link, or node, is pretty straightforward. It's got 2 main parts. Data, this is where the actual information is stored, could be a number, a word, anything really. Next node address, this is like the little connector that tells us where the next link in the chain is. It basically points to the memory location of the next node. So, we chain these nodes together, one after the other. The first node, our starting point, is called the head. Each node points to the next one in line, and since the last node doesn't have anyone to point to, its next node address simply points to null, signaling the end of the line. Now, let's step it up a notch with doubly linked lists. These are like chains that have an extra connector on each link. Instead of just pointing to the next link, each node in a doubly linked list has 3 parts. Previous node address, this points to the node that comes before it in the list. Data, same as before, this is where we store the actual information. Next node address, and this points to the node that comes after it. So, if we have a node called John 2, its previous node address might point back to a node called John, and its next node address might point forward to, say, a node called Jane. It's like having two-way traffic on our chain, making it easier to move back and forth through the list. Finally, let's talk about circularly linked lists. Imagine taking that chain and instead of leaving the ends loose, we connect the last link back to the first one. That's what we call a circularly linked list. It forms a circle. There are 2 ways we can make this circle. One way is to just connect the very last link back to the first one. That's called a singular circular linked list. It's like a one-way loop, we can keep going around and around in one direction. The other way is to connect the last link to the first and the first link back to the last. So, it's like a 2-way loop. We can go forward or backward through the circle. That's called a doubly circular linked list. Let's talk about stacks. Imagine a stack of plates. You always put a clean plate on top of the stack, and when you need a plate, you always take the top one first, right? That's the basic idea behind a stack data structure. It's called last in first out, or LIFO. The last thing you put in is the first thing you take out. Make sense? So, let's say we start with an empty stack. Now, we want to add the word hello. Then we add world, so world goes on top of hello. Next, we add string, and it goes on top of world. Finally, we add program, which becomes the new top of our stack. Now, when we want to remove something, we always remove from the top. So, the first thing we take out is program, because it was added last. Then, if we remove again, we get string, and so on. Just like we had different flavors of arrays and linked lists, stacks also come in a couple of varieties. First up, the static stack. Think of this like a stack of trays in a cafeteria. There's only a certain number of trays available. Once the stack is full, you can't add any more. So, if our static stack has a size of 4, we can add 4 elements no problem. But when we try to add a 5th element, nope, it's full. The stack won't budge. Then we have the more flexible, dynamic stack. This one is like a magical stack of trays that can grow as needed. We might start with a size of 3, but if we need to add a 4th element, no problem. The dynamic stack expands to make room, changing its size from 3 to 4 to accommodate that extra element. This dynamic nature is super helpful when we don't know how much data we'll need to handle beforehand. Now, let's talk about the things we can do with our stack, the actions we can take. First up, we have push. Imagine gently placing a new plate on top of the stack. That's what push does, it adds a new element to the top of our stack. Next, we have pop. Now, we want to take a plate off the stack. We always take the top one, right? That's what pop does, it removes the top element from the stack. Sometimes, we just want to peek at what's on top without actually taking it off. Like, is that a dinner plate or a salad plate? That's where peek comes in. It lets us take a look at the top element without removing it from the stack. Then we have is empty. This one's easy, it just tells us if our stack is empty or not. Is our plate holder empty, or are there any plates left? Finally, we have size. This tells us how many plates are in our stack, is it just 1 or 2, or do we have a whole bunch? So, those are our basic stack operations. Let's talk about queues. Imagine you're standing in a line, that's a queue. It's called first in, first out because the first person in line is the first one to get served. Queues work the same way in computer science. We add things to the back of the queue, like a new person joining the line, and we remove things from the front, like the person at the front getting served and leaving. Now, the simplest type of queue is a simple queue. Think of it like a line with a fixed number of spots. Let's say our queue has a size of 4. We add A, then B, then C, and finally D, our queue is full. Now, when we remove someone from the front, A leaves the line. But here's the thing with simple queues, even though there's an empty spot now, we can't just add someone new to that spot directly. We have to wait for B, C, and D to move up in line first. That's where a circular queue comes in handy. It's like a line that forms a circle, no more fixed front or back. We can add and remove from any point in the circle. So, in our example, when A leaves, we can immediately add someone new to that empty spot, even though B, C, and D are still in the queue. It's much more efficient. Now, queues can get even more specialized. Imagine a line where people with priority get to go first, even if they came later, that's a priority queue. Each person in line has a priority level, and the person with the highest priority gets served first, even if they were at the back. Then we have double-ended queues, or deeks for short. Imagine a line where you can join at either end, you can be the first in line or the last in line. Deeks let us add and remove elements from both the front and the back. Now, let's switch gears a bit and talk about nonlinear data structures. Instead of a straight line like a queue, imagine a tree with branches. That's what a tree data structure is like. It starts with a single node at the top, kind of like the trunk of the tree. This node can have branches, or child nodes, connected to it. Each child node can then have its own children, and so on, branching out like a real tree. Each node holds some data, and the connections between them create a hierarchical structure. Let's break down the different parts of a tree, kind of like identifying the roots, branches, and leaves of a real tree. First off, we have nodes. These are like the individual points on our tree. Each node holds a piece of data, like a name, a number, or anything really. Now, to connect these nodes, we have edges. Think of edges like the branches that link one node to another. They show us the relationships between the nodes. At the very top of our tree, we have the root node. It's like the main trunk of the tree, it doesn't have any parents, no nodes above it. And just like a real tree usually has one trunk, there's only one root node in a tree data structure. Now, any node that has other nodes connected below it is called a parent node. It's like a parent with one or more children. And those nodes connected below are called child nodes. Nodes that share the same parent are like siblings, we call them sibling nodes. Then we have leaf nodes. These are the nodes at the very bottom of the tree, the ones that don't have any children of their own. They're like the leaves at the ends of the branches. Sometimes, we want to talk about the route we take to get from one node to another. That's called a path. It's like following a series of branches and nodes to get to our destination. A subtree is like taking a section of our tree, it's a smaller tree contained within the larger one. Now, imagine tracing back from a node up to the root. All those nodes along the way are called ancestors. It's like looking at the family tree of a node. We also have levels in a tree. Think of it like floors in a building. The root node is at level 0, its children are at level 1, their children are at level 2, and so on. Finally, the height of a tree tells us how tall it is. We measure it by counting the number of edges from the root node down to the deepest leaf node. It's like measuring the height of a real tree from its base to the highest branch. You know how there are so many different kinds of trees in a forest? Well, it's the same with trees in computer science. We've got a whole bunch of them, each with its own special name and purpose. We've got red-black trees, heap trees, binary trees, segment trees, and these are just a few examples. There are tons more out there. It's like a whole forest of data structures. Graphs is the next data structure in our list. Imagine a bunch of dots connected by lines. That's the basic idea behind a graph. It's another way to organize data, but unlike trees, graphs are more free-flowing. Those dots are called nodes or vertices, and they represent things like people, places, or concepts. The lines connecting them are called edges, and they show us the relationships between those things. For example, if our nodes are cities, an edge might represent a road connecting two cities. Now, when two nodes are connected by an edge, we say they are adjacent nodes, like neighboring cities connected by a road. It's like they're right next door to each other. Sometimes, we might have a node that's all alone, not connected to anything. That's called an isolated node. It's like a remote island with no bridges or ferries. You can't get there from here. And then we have self-loops. That's when a node has an edge that loops back to itself. It's like a road that starts and ends in the same city. You might wonder why anyone would build a road like that, but it's actually pretty useful in graph theory. The degree of a node tells us how many edges are connected to it, like how many roads lead into a city. It's a way to measure how connected a node is to the rest of the graph. Now, graphs can be undirected, meaning the edges are like two-way streets. You can travel in either direction. In this case, the degree is just the total number of connections. But graphs can also be directed, meaning the edges are like one-way streets. You can only travel in one direction. In this case, we talk about in degree, how many roads lead into a city, and out degree, how many roads lead out of a city. Finally, a path in a graph is like a route we take from one node to another, following the edges. For example, a path from node A to node C might go through node B along the way. It's like a road trip, but instead of using a map, we're using the graph to navigate. Okay, just like we had different types of trees, graphs come in different flavors too. First up, we have the simple graph. It's like a basic roadmap, no fancy stuff. It has a few key rules. No two cities are connected by multiple roads, no multiple edges, the roads are two-way streets, undirected, and there are no roads that start and end in the same city, no loops. Then we have weighted graphs. Now, imagine each road has a number associated with it, like the distance or the time it takes to travel. Those numbers are called weights, and they give us extra information about the connections between nodes. Next, we have directed graphs. Now our roads become one-way streets. Each edge has an arrow, showing us the direction we can travel. It's like a city with a lot of one-way streets. On the other hand, undirected graphs are like road maps with only two-way streets. The edges don't have arrows, so we can travel in either direction. Now, imagine a road trip where you end up back where you started. That's like a cyclic graph. It has at least one loop, a path that brings you back to the starting node. Finally, an acyclic graph is like a road trip with no roundabouts. You can't loop back to any previous point. There are no cycles in the graph. And that's a wrap for our tour of data structure basics. I hope you learned something new and had a little fun along the way. Please like, subscribe, and hit that notification bell so you don't miss out on any new content.